The problem with using a hash table is, as we've seen, each item ends up in a bucket. We don't know which one. And so what we're going to do is do a pretty natural change, which I'll call uniform partitioning. So in this approach, what we'll do is create buckets that are contiguous regions of space. So for example, I could subdivide my space into 16 different regions. This is sometimes these buckets or regions are also known as bins. And this is just an example of a 4x4 grid of such buckets. And effectively, what we've done here is we've partitioned the space. So as a result, that means that we know that any item with this xy coordinate will be in this specific bucket. Okay. So question for you. If we wanted to find the closest point to the space horse, how many different points do we need to look at if we have this partitioning scheme? And similarly, which buckets do we need to iterate over to find all the points in the green range? Okay, so the first one, the answer is we only need to look at these 3 points. So basically what we would do is compute the bucket number of horse and see it's in bucket 1, and then say only look at the points in bucket 1. And they would be stored there because that's what we're doing. We're storing each item in a list of items that are in that bucket. And then when it comes to iterating over the green rectangle and finding all the points that are inside the green rectangle, there's no need to look in bucket 13 or 11. We only need to look at the points in 5, 6, 9, and 10. So we would go to bucket 5, let's say it's implemented as a list or whatever, and we would look at this point, this one, this one, this one, this one, and we'd be adding them to some results list. When we got to bucket 10, we'd look at like this point, 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 and so forth. Now you might say, well, it seems silly. Like, why are we looking at all these points? These are pretty far from the box. And so what you could do is subdivide the space into yet smaller pieces if you wanted. And it's a trade-off. Alrighty. So ultimately, this idea is that we're partitioning our space into uniform rectangular buckets, and a typical implementation would have the container itself, whatever you want to call this thing, a uniform partitioning table, whatever, and it would compute the bucket number for points. So rather than using the object's hash code, each object would provide a getX and getY method, and when it gets inserted into this uniform partitioning table, it would compute the bucket number at that time. Now I'll note something kind of interesting about this approach. It's sometimes called spatial hashing. I see that term online. I love that term. But what's interesting is it just doesn't seem to be official. But in the game dev community, the game development community online, it seems like a common term. But outside of that, not so common. So that's our first approach. Now, a question for you is, what is the runtime if we start thinking about asymptotics, just try and bring to bear our formal knowledge? What will be the runtime for nearest, say this horse example, assuming that the points are evenly spread out? So we have n points across these 16 buckets. What's the runtime for nearest going to be? Okay. So it turns out the correct answer is theta n. So it's still theta n. Why? I mean, it seems like a little strange that we did all this work, right? If we go back to our original scheme, it was theta n because we had to look at all the points. And now that we've subdivided the space, it's still theta n, assuming the points are nicely spread out. And the reasoning is that, on average, the runtime is going to be, in this case with 16 buckets, 16 times faster than if we didn't do the spatial partitioning, but n over 16 is still theta n. However, I will note that even though it is still theta n, it often works pretty well in practice, though we'll see some better ways of doing this. Okay? But just be aware, this is one approach you can take, and it's perfectly valid. Okay? And what we're trying to do today is just kind of model different ways we might try and approach this totally new set map operation implementation. Okay? So that's this approach, and so we'll move on to more search tree analogous approaches next.